Hi everyone, my name is Kyle Franson. I am a postdoc at UC Santa Cruz. Let me make sure I'm standing in the right spot. I'm really excited to continue building upon this theme of using astrometry to inform our exoplanet imaging searches. I'm going to sort of hopefully breeze through some of the results from a program that I've led over the last several years, mostly while I was a PhD student. And I want to especially emphasize some of the future directions that I'm especially excited about. I really want to pitch all of these exciting results, including the amazing results from the OASIS survey, as kind of the first generation or the very beginning of this strategy of astrometry-informed target selection. So I certainly don't need to convince this crowd that high contrast imaging is one of the most powerful techniques that we have to characterize planets around other stars. The community so far has imaged around a few dozen giant planets on wide orbits. Each of these discoveries offers clues on their potential formation through their orbits, through their atmospheres, through demographic trends. And we're just getting to the point of being able to tease out on an object-by-object basis and sort of broader trends, which planets seem to be more consistent with formation through a core accretion-like scenario versus disk instability versus maybe some of these objects are forming through the star formation process. And I actually think that this is rather remarkable given that we as a field face significant headwinds, which is that nature has not been generous in gifting us tons of really easy to image planets. It depends on where you kind of draw the box, but you know, for sort of 5+ Jupiter mass planets, 10+ AU, you generally get occurrence rates of order a few %. And so this means if you run a large blind search targeting hundreds of nearby young stars in a kind of blind fashion, you'll generally get sort of maybe 1 to 2 planet discoveries, really valuable demographics information, but you also have to sift through lots of non-detections. This story might change, by the way, as we access new realms of parameter space. I'm thinking about those 40 candidates from Aaron's talk yesterday. Another challenge is that most imaged exoplanets don't have direct mass measurements. So this plot here shows the current sample of imaged planets and brown dwarf companions and the masses, in air quotes, and orbital separations of that current sample. And for most of these objects, we have to infer their masses using evolutionary models. And so that folds in all of the uncertainty in formation condition, right, like hot start versus cold start versus warm start. There's also uncertainty, right, in terms of the ages of these companions. And so we might not be sure whether something is 5 Jupiter masses or 20 Jupiter masses. But over the last few years, it's really been amazing to see the measurement of these benchmark companions with dynamical masses, where they're at close enough separations to exert enough reflex motion for us to actually be able to make those direct mass measurements. And on an object-by-object basis, as we heard about in Emily's talk, these objects really offer us some of our best opportunities to constrain the planet formation process. We can test evolutionary models with these objects, but also they just serve as benchmarks, right? We've pinned down their masses. That part is solved without needing to go to the age. One thing to emphasize is that we've only scratched the surface so far in the planetary regime. And so we want more of these planet benchmarks. And so astrometry from Hipparcos and Gaia has clearly proven to be a really effective strategy to getting more of these planet dynamical mass benchmarks. And the idea is we're going to intentionally bias our exoplanet imaging search. So instead of sort of surveying tons of stars in an unbiased fashion, we're going sort of straight to the stars that are giving us the dynamical evidence that are signaling to us in a proper motion change between Hipparcos and Gaia that there's something there. And so I've been leading a survey. An advantage of this approach as well is that these accelerations then enable the measurement of dynamical masses. And so we're just now wrapping up a survey targeting stars that show these astrometric accelerations and trying to image planets around them. And so we're currently in the throes of publishing all of the data that we've accumulated over the course of the survey, which includes high contrast imaging data. It also includes some ancillary data that I think is going to be really useful to the community. So the primary false positive for for these astrometric accelerations are stellar mass binaries. Because you can imagine, right, given an astrometric acceleration, it could be produced by a closer separation lower mass thing or wider separation higher mass thing. And ideally, we don't want to spend tech time on wider separation binaries. And so we've been going through and vetting over 1,000 accelerating stars of these stellar mass binaries, finding about a quarter of them to be produced by binaries. We're also obtaining high-resolution spectroscopy of hundreds of accelerating stars, and all of these data are going to be made public in kind of a catalog form. And I'm really excited about this. One thing to remember is that these non-detections mean that there's something there, right? We've pinned down the source of the acceleration a bit. And so that'll be useful for sort of future exoplanet imaging searches. It's also going to be useful in the Gaia DR4 era, because many of these accelerations are going to be caused by closer separation planets that will eventually be revealed in some fashion within Gaia DR4. There's a utility for planet validation here. So with these vetted accelerating stars, we then sort of prioritize the young ones and try to search for planets around them, obtaining high contrast imaging sequences. In total, we've obtained high contrast imaging, if we sort of isolate the young sample, of 34 young accelerating stars. And so the question is, you can already get a sense that the scale of this survey is smaller than the kind of hundreds of targets surveys, demographic surveys. But the question is, how do we do at improving the efficiency of imaging new planets? Well, the first discovery from this survey was HIP 21152b. This is a brown dwarf companion that I actually talked about at the Spirit of Leo in Leiden. It's the first imaged brown dwarf companion in the Hyades cluster. It has an age, kind of an intermediate age of 650 megayears. I should point out, too, that this has been kind of a theme with some of these discoveries, that multiple teams arrived at this discovery, including one team led by Masayuki Kuzuhara, who's here. And as we as Emily alluded to in her talk, this is one of these brown dwarf companions that's over luminous or under massive compared to evolutionary models, one of these younger kind of T-dwarfy or LT transition objects. The next discovery from this program, of course, is AFLEP-B. We've heard about AFLEP in Emily's talk and saw some amazing results with NIRSPEC in Jerry's talk yesterday. AFLEP-B is the lowest mass imaged exoplanet with a dynamical mass measurement. And one of the more exciting elements of the discovery of this planet was the sort of simultaneous discovery from multiple teams arriving at this planet at the same time with different data sets and different kind of instruments. And so this has meant that this planet has been really well characterized kind of right from the outset. And so now we're at the place where most of the orbital parameters of this planet have been pinned down extremely well. The dynamical mass is 3.5 Jupiter masses. And again, this is a dynamical mass measurement, so we've pinned down the mass, which for a beta-pic moving group kind of like age is consistent with hot start evolutionary model predictions, or maybe warm start model predictions if the planet took a little bit of time to form, if the planet's maybe younger than its host star. It's orbiting on, it has a semi-major axis of 9 AU, so it's kind of a Saturn-like orbit. It's a circular orbit, and its orbital inclination is consistent with the projected rotation axis of the host star. And so this is kind of reinforcing some of the already emerging trends among the imaged exoplanets. Its atmospheric metallicity is enhanced as well. And so these bits of evidence are suggestive of this planet forming through a kind of core accretion-like formation scenario. It's been really remarkable to see this kind of comprehensive picture of this planet be uncovered over the last few years. And I want to sort of highlight that this has really been a community effort to characterize this planet over the last couple of years. So there's been dedicated retrieval and forward modeling analysis of the planet's atmosphere, and archival recovery of the planet, JWST observations of the planet, gravity observations, high-resolution spectroscopy. And of course, we've heard about some additional data sets that are on the way. And so I wanted to take just a quick sec to highlight one of these follow-up programs, which was a Cycle 2 Director's Discretionary Time program that William Ballmer and I led. I remember when this data came in being so amazed by the remarkable recovery of this planet. But now NIRSPEC is kind of blowing this out of the water, right? And so to emphasize the difficulty of this detection, I'll just note that here we're staring through a coronagraph. So the throughput that we're correcting for is 7%. This is just another node in this story of JWST outperforming some of the initial expectations that I think many people in the community had prior to launch at these kind of small separations. Okay. So with those discoveries in hand, we can now take stock and assess how have we improved the efficiency of imaging new exoplanets. And so out of a 34-star sample of young stars, we have one new planet discovery, one new brown dwarf discovery, which is about 1/10 of the stars that has historically been required to achieve a similar number of discoveries. We're estimating a 10-fold improvement in planet discovery efficiency. And one thing I want to emphasize here is this is really kind of a pros and cons between large unbiased surveys and these astrometry-informed exoplanet imaging programs, because we're intentionally biasing our sample here. And so if we want to get occurrence rates at wide orbits as a function of host star mass and stellar metallicity and semi-major axis, there is no replacement for a large unbiased sample. But if the goal is planets that can be dynamical mass benchmarks and sort of great targets for orbital and atmospheric characterization, astrometry provides a fast track to achieving those discoveries. And I want to spend the last sort of couple minutes here talking about some future directions that I'm especially excited about. I want to pitch all of these exciting results as the first generation of this astrometry-informed exoplanet imaging search. So if we zoom out to sort of assess where we're at, right, we've significantly expanded the sample of these benchmark companions. One area of parameter space that's really exciting is these older kind of solar system age planets, where JWST has really been a beast at accessing these coldest of atmospheres. And we have two benchmarks, Epsilon b and 14 HER-C, at those solar system ages. Those are both hinted from radial velocities and also are revealed in astrometric accelerations. But the sample of RV exoplanets that are at wide enough separations around really nearby stars to be accessed from JWST is relatively limited. And so astrometry provides a really promising route to adding to this sample of benchmark companions at older ages. And so I'm currently leading a Cycle 4 program targeting 5 of the nearest accelerating stars where they're strictly prioritized based on for proximity and consistency with wide orbiting planets. And I just want to highlight that we've started to get data on some of these systems. So this is the first sequence taken in the survey. It's 6 degrees away from the galactic center. But it's actually not that bad in terms of sort of contamination from additional sources. And if we sort of plot up the sources on a CMD, we see that one of the sources is red, right? It's exciting, right? Next F-Cindy, right? No, it's a galaxy. But I'm really optimistic about this strategy, especially going forward, and the prospects of this to expand the sample of the nearest atmospheric benchmarks at cold temperatures. And then finally, Gaia DR4 is poised to really change the game here in astrometry-informed exoplanet imaging searches. I don't think it's exaggerating to say that DR4, the impact that Gaia DR4 is poised to have is similar to the impact that Kepler had a decade ago. And so just to illustrate why I think that Gaia DR4 is really going to significantly expand the pool of potential targets for this type of astrometry-informed imaging search, here's the current sensitivity to astrometric accelerations around AFLAP. So anything above this curve shows up as a 3 sigma or higher astrometric acceleration. This is what we get when we combine Hipparcos and Gaia DR4. So it pushes down sensitivity across the board. But this doesn't tell the full story of the additional targets that are going to be opened up when DR4 comes out at the end of the year. This region shows where planets would be recovered just within Gaia. And so all the stars that are sort of too faint to be in Hipparcos is magnitude limited to kind of 10 or 11 mag, are all going to suddenly become fair game for this style of informed direct imaging search. And that'll come at a time when all of these different new high contrast imaging instruments, very non-exhaustive lists, are being developed. So my prediction is that this is going to lead to a significant expansion in the population of these benchmark planets at lower masses. And in the longer term, Gaia DR5 will sing with the 30-meter class telescopes. That's all to say that the future is very bright for this style of astrometry-informed imaging survey. Thank you.
Thank you. We have time for one question. Yep.
Hi, thank you, Kyle. Oh, great talk. So I'm also, my question is radial velocity measurements. I am taking radial velocity measurement for the target that are showing acceleration as well. I think that's the first purpose is to check whether the system is binary or a stellar binary or not. But as an additional benefit, so if you have many RB measurements with a baseline over a few years, the data are useful to better determine the mass of the your target. So my question is, how many RB measurements are you taking? And so what is the time baseline of your RB?
Oh, for the binaries?
I think you are taking RB measurement before imaging your target, right?
Oh, yeah. So we're generally, there's a couple of flavors of this. So we have an RV monitoring campaign for a handful of accelerating stars. I didn't really talk about this, but these are accelerating stars that we've imaged with the high contrast imaging to characterize the sources of those accelerations. And that's more of a kind of precision monitoring campaign. We've also been trying to get sort of high-res spectroscopy, not precision RVs, for hundreds of accelerating stars, and generally trying to kind of follow them up on a sort of year cadence-ish. But that's more for sensitivity to single-line spectroscopic binaries versus teasing out the RV trend.
Okay, so thank you, Kyle.